So, allow me to a little more what you call mix how to make a thermally useful enclosure which uses standard what you call commercial extrusions and so on. The issue being in the just in the previous lecture I have shown you several enclosures and all which are taken directly from the industry. Now, not every time they start with absolutely new fin designs and so on, because these have been routinely being used for such a long time. Now, if you have a look at a typical heat sink from the manufacturer, you will notice here that several of these profiles are already been in use for quite some time. You have seen this here. So, you have something which is typically around 100 mm wide. So, this is the 100 mm wide heat sink, and then there is a 4.5 mm what do you call base for this aluminum, and then there is a this thing. Now, I will try to move it here. Now, have a look at this heat sink which is about 115 mm wide, there is a 10 mm thing. Now, if you see the sample which I have here, sir, show them the sample. That heat sink which is there probably belongs to one of these things here. Can you see here this big monster here, and in fact at the base now it is a little bigger, it is 18 mm thick. So, I will just take these things off. See that end, this is not a manufacturing defect, it is not a manufacturing defect, it is just that the extrusion has come like this, and maybe during our handling it has bent and all that. Now, coming back to our this what I call sample here, such I will call them standard or generally replaceable heat sinks are available like this. Why people use one of these profiles is that something nearby will already be available, and if you are in the what you call you are designing for something, we know very well somebody else also probably has a same type of what you call requirements, and somebody in the world has made something is a little closer to that, and the advantage of using this is they are not very expensive, and once if you buy a profile like this and keep, you will be able to use it without any issue at all. So, I will just try to go down, and you see here one more important thing is, if you are to make your own, we may not be able to achieve this detail that they have given here. You see the detail there at the left, detail there at the left is some what you call attempt has been made to increase the surface area by providing additional ridges. Now, the next question you may ask is, sir, does it really help or how do you do? That is for you to probably make a model and then try to compare what they have with what you have, and there is no IP involved in checking these proportions, and you are adopting something similar to that. Now, if you again look back at this small thing here, can you see here? These ridges are a little offset. Is it good or bad? It is for you to decide whether it is good or bad. From my point of view, I feel they have tried to make it somehow they have optimized the load involved in creating the extrusion. So, if you just put a tapered extrusion and give a few what you call cuts on this side and that side, no, it may or may not be useful. But however, if you see this corner here, you see here it is a little about what exactly it is on the other side, but the way they have offsetted, and probably while the detailed drawing does not clearly give you the details, probably the base is a little wider compared to when it goes on top, and we need this specific type of design because these are all extruded in long lens. I am not very clear what is the current standard. In the shops you will get them about a meter long, but then in the extrusion industry they are all made for building standards. Building code requires that at least you start with something typically 3 to 4 meters long. So, you have 4 meter machines and 3 meter machines. Now, if you can see the samples which I have put there, these are all samples which have been taken from the building industry. I do not know what exactly this component is. There was some construction going on, I just picked it. So, it probably looks like extrusion for a window or something like that. You see the mitered or 45-degree joint there. So, two of them can be joined together and you can make something which is a little like this. Unfortunately, that element of detailing is no way useful for us. They have made some arrangements for something to slide inside. There is a something which has a some extrusion, I mean one angle, something which will go here, something which will go here, and they meet perfectly, and then you can assemble things. These are not useful for us in any way when we talk about our own electronic extrusion. So, something called the electronic extrusions what you see in this catalog have been specifically developed with our concerns in the mind. So, if you go down you have very simple straightforward things like this. See, this one has only a U-shaped base, so that will give a general what you call advantage over it. Then ridged profiles which I have shown you already, you see here they are directly on opposite directions. There are these what do you call ridges here. You have noticed something which is very different from it. Here it is tapered. So, somebody has probably expect the actual electronic user like you and me have insisted that they want something which is a heat sink should be much more effective than now. You notice this is slightly different from what we have seen there. That same what you call ridging is available there, which is a radius ridge, which has probably some advantages, and to make the fin effective it is much wider at the base and much narrower at the top. Now, whether it is calculated or not depending on the manufacturer, I will call them the vendor with the actual user which is the designer. I expect that since this tooling is very expensive, somebody has done the homework, and these days homework is directly by carrying out a simulation probably in a computer, and then the basic part of the simulation is that they should physically analyze which is good for them. You understand, no? Some of these things if you see are very thin, so not very effective, and then it gives you a general indication that these are probably meant for simple natural convection, not meant for forced convection. When you come to forced convection, you will notice that there are wider like this, okay, and there is little more space here. So, I will try to go back to the whole thing we have done. So, not by just looking, but also if you now go back to this catalog, you see here very complicated things are. Have a look at this thing, have a look at this. I am not very clear what it is for, but I expect it, yes, it does have a purpose. You have extrusions in which I do not know whether it is a support or whatever it is. You can go back to the catalog. This catalog is taken from electronic. Electronic has probably developed these things for military and other professional people. So, they will give you a lot of data if you directly interact with them. These are a little few of them which I have been showing you here. Seen this, no? So, I will just talk about one small thing. Sometimes occasionally I find while I am not a nitpicker, if you have a look at this, I hope I will be able to go to we are partly here. You will see one or two what I feel are obvious what you call a few things which they have overlooked. One of them is while the small notch here does seem to make some difference, you see here. See that notch there? It is likely to seriously interfere with the heat conduction pattern. So, anything which is here, see suddenly this whole thing, this is the small bridge that is available for us. You have seen this is the restrictive bridge. So, any heat which comes here has to cross over this what you call narrow path here. Moment you attempt to cross over, all these things now will not be that effective anymore. So, if they had removed this and then optimize the location of all these things, then these other things also can be used. But then from the purely from the product design point of view, probably this was required for some alignment or I do not know whatever it is. So, all this heavy mass here, no, it is really not as effective as we want to have a look at it. So, it is for you now, if you can include this in your what you call thermal model, it is good. Otherwise, best and simple way is take a section of a approximate length which are like to use, mount a few power devices, keep them in the linear region and you excite them and see what will be the, in your conditions, what will be the thermal resistance of a thing like this. Now, I will try to close this and see one more. You see here, this I thought I should be able to, which I was just talking about it. See, what they have done is this particular small heat sink here, I will enlarge it later, you will be able to see. They have given details of, this is from an earlier era where we used to have the TO3 packages, and then you see this is the probably the most important thing I would like to point out to you. Allow me to just play around a little. Got it. Seen something here? Air velocity, then you have power dissipation, and then heat sink rise above ambient, and then thermal resistance, all of them have been conveniently plotted here. So, you will notice that if the heat sink temperature it keeps rising. So, they have given for 621 and all that. How to read it, they have given on the other side. So, instead of my talking about it, I suggest you try to read it about yourself. As you increase the air velocity, the thermal resistance comes down for both 621 and 623. At initial stage, typically around 50 degrees centigrade per watt will be there, and then as it goes down, I am sorry, the thermal resistance will keep coming down. You will notice is that after it crosses typically about this 300 figure, increasing the air velocity does not make much of difference. So, in my other Schoenholzer's lecture, there they have typically given 6 meters per second. Anything which goes above that, it is just adds noise and turbulence and does not serve any purpose. For a given heat sink, it looks like these figures are quite valid here. They have just given it generally how to mount it, and then generally they have given about what is the length, and then also a little bit about that 621 and 623 talks about these two models 621 and extrusion profile 1327. They have cut it here. So, then they have given details at all. Low profile, you see the issue is that basically it is a very extremely low profile device. So, we need to now check. Now, if you go back here, you see here at the left here and the left top, you have the heat sinks meant for stud mounted devices. So, we have a stud mounted device, and I am not sure what it is. And then one more thing have you noticed here, the anodic layer has been removed here and it has been machined clean. Two variants are there. One is you mask it such that it does not get the color while coloring it, or what do you call, adding the dye to the other thing. Another thing is you get it in the proper condition, because manufacturing is easy, masking is always tough. After you get it anyway, since the other operations are required including a tapping and things inside, you lightly machine it, and in the same way you can also probably lap it. The moment you do that, you have a beautifully fantastic mounting surface, and then you can do whatever you want with it. So, this is a part number 300K they have given here. Now, extreme right side, for each length mounting holes, thermal performance they have given. You have seen that. Natural convection versus forced convection. If you give this much of what do you call, I am not very familiar with the units, down it is explained. For a stud mount, if you do not use anything for a given length, you typically get about 70 degrees centigrade at 15 watts dissipation, and here you see here in forced convection 2.5 degrees centigrade per watt. So, you can keep multiplying, and then you see here as the length increases, these numbers keep coming down. You can come all the way up to almost 1 degree centigrade per watt, and they are not very heavy. Then you see here the length is not very, what do you call, is not very long. So, we have more what do you call design data about these things which are circular. So, if you go down, you can so any of these manufacturer's catalog gives details about more and more details about how do you mount these devices here, and then you see here there is something very what do you call interesting or whatever it is. So, if you now look at these type of heat sinks, this one I will see if I can enlarge it properly. Unlike the earlier other things which I have shown, this has fins on both sides, and width is 60 mm, usable length is about 65 mm, and then this length of it comes to 120 mm of length. Okay, I will take this as height of the heat sink and the width of the heat sink 120 by 66, and then you have lengths of 76 mm and a little nearly double the length of it. So, you see here this heat sink performance, no, I suggest you separately look at it by in your hand, and you see that the air velocity as it increases, how the thermal resistance come down, and then how the heat sink what you call dissipation and all now increases. These details are given here for most of the commercially available power semiconductors. You have seen this. Then we have something for the various rectifiers and so on. So, this is a huge catalog. Deliberately I have taken an old catalog, so that the samples we have approximately coincide with that. Now, this again looks a little like this other heat sink we have here. You see this, we have other heat sink here, and you see here now you will probably appreciate. Now, if you come back, we again have a fan which matches this. Now, you see here they are nicely made such that nicely they fit here. So, we have a fan which is probably a, what do you call 235 mm square. You can mount all these things. There are mounting holes here and huge amount of what do you call space they have given, such that we can mount things for various semiconductors, generally supplied with blank holes, and you can attach fans directly, and then if you are both in the push pull mode, this is also one of the interesting things. I hope the catalog now shows, yeah, you see this. I will draw your attention to this particular picture. Unlike some of the other heat sinks which I have shown there, you have noticed the mounting flanges are near the tip of the profile. So, these are probably the ones that are used in power semiconductors, power electronics equipment, while this part faces the wall. You have seen this, no? This part faces the wall, this part can be used, this flange can be used for mounting, and all your semiconductors can be mounted on this face, and if you put a cover here on the other side, your equipment is ready. And very miraculously, these dimensions, in the case this is about 5 inch, probably it follows the panel mounting standards. So, I have the patience to go through all the catalogs, or one more which intellectual property is to be protected, but just like in the case of our academic this thing, we know published literature we are expected to already verify and then acknowledge in case somebody has already done the work. You cannot publish, somebody else has published, however you can acknowledge and build on it, the delta thing. Same thing it is with our design thing also. In the beginning somehow you have to find out your needs. Once the needs are over, comes the important thing. Instead of talking it as a patent such, you need to look for the prior art, saying how is it others are doing. And in the prior art, while I am not advocating violating of IP, we can show how others have already been doing it. Only thing is you cannot claim you cannot get a IP on that. So, typically there is one of them. So, if you take a standard drive, there are any number of ways you can mount these what you call heat dissipation things.